This question is asked in gate 23 of instrumentation. This is from network subjects and from Thevenin theorem concept. The question is, in the circuit given, the Thevenin equivalent resistance RTH across terminal A and B is dash ohms. So you are supposed to find RTH across this terminal, right? So you can see, student, this is a network having only independent sources. There are no dependent sources, so our job is quite easy in this case. So what we do is, while finding RTH, all the ideal voltage sources, so they are replaced by short circuits. All the ideal current sources, they are replaced by open circuits. So if I do this, so how does my circuit will look like? So let me draw the circuits. So this is your 1 ohm, all resistors are 1 ohm, right? Yeah, so then this voltage source is sorted. So I was placing it by sort. This is 1, this is also 1. And then this current source is open, then this is 1, all right, then this is 1, again this current source is open, and then this is 1 and this is 1, all this, and we are supposed to find RTH from this terminal, right? All these resistance value are R only, 1 ohm, so 1 ohm, 1 ohm, 1 ohm, this also 1, right? So you see, ideal voltage source sorted, ideal current sources, they are open circuited. So now if we see, so this segment is replaced by short circuit because 0 ohm parallel with 1 ohm is again 0. So now we are left with, and these are all dummy element I can tell which are being open circuited. So these paths have no role at all. So if I see RTH, so then 1 and 1 they are in series, this is 2 ohm. And this 1 and 1 they are also coming in series, 2 ohm. So if I observe RTH, what RTH is, so you can say that 2 ohm is in parallel with 2 ohm, then the answer is 1 ohm. If I am observing from here, there are two equivalent paths from this terminal. There are two equivalent, one is this path, other one is this path. So this path resistance is 2, 1, 1, 2, because this is sorted means overally it is 2. So from this there are two paths. This path is 2 ohm and this path is also 2 ohm. And they are in parallel, 2 parallel 2. Answer is 1 ohm. Pretty simple and straightforward question. Answer is 1 for this. This question is asked in gate 23 of instrumentation. This is from network subjects and related to resonance concept. The question is, in the circuit zone, omega R1, R2, L value are given. The capacitance C for which Y in is purely real in millifarad is how much? Okay. So we are supposed to find what is the value of this capacitor so that this admittance Y in is purely real. What is the meaning of purely real? The meaning of purely real is the circuit is operating under resonant frequency or under resonance condition. Because in general, impedance and admittance are complex quantity. So if the imaginary part is going 0, if they are purely real, it means that the circuit is under resonance condition. In other words, we are supposed to find what should be the value of this C so that this circuit is operating under resonance condition. That is what the question is. So we know, students, like whenever we have a series RL is in parallel with series RC, whenever we have a series RL is in parallel with series RC, then there is a condition called R square is equals to L by C. If this condition satisfies, then this admittance or impedance is purely real for all frequency. This is a very popular and a standard circuit, students. Whenever a series RL is in parallel with series RC, and if we satisfy the condition R square equals to L by C, then the circuit operates in resonance at all frequencies. It really doesn't matter what is the frequency, omega it is 10, 20, 30, 40, it really doesn't matter. In all frequency, it satisfies that the circuit is under resonance condition. We need that. So here omega is given 100 pi. It doesn't matter actually whether it is 100 pi or 1 pi or whatever it is. It is completely irrelevant as far as this question is concerned. So at all frequency, the circuit will be under resonance if we satisfy this condition. So C is equals to L by R square. So L value is given 7 millihenry, and this is 7 and this is 2.2. So it will be coming on milli units because it is millihenry I am saying. So 7 by 2.2 square you will get, R square it is there, isn't it? So if you solve this, this is coming as 1.44 millifarad. So the answer is 1.44. But students, if you don't know this standard results what I am saying, and if you go by actual procedure, how this actually there is a proof actually how it happens in theory, we give this. and if you go to that proof, it is hardly it is not less than 15 to 20 minute task if you don't do any mistake in between. It is very lengthy actually. That's why, because this activity is very standard, repeatedly coming in GATE exam, we always suggest to memorize these standard results. So by referring that, the answer is 1.44. This question asked in GATE 23 of instrumentation. This is from network subjects and related to transient concept. The question is, the RL circuit with R equals to 10 kilo ohm, L equals to 1 millihenry is excited by a step current of I0 ut. At t equal to 0 minus, there is a current of IL equals to I0 by 5 flowing through the inductor. The minimum time taken for the current through the inductor to reach 99% of its final value is dash microsecond. So what data student given is that at t equal to 0 minus, there is a current. That means the inductor having the initial current. So IL of 0 minus is given as I0 by 5. And it says step input case, students. In this case, the inductor current is given by the well-known equation, which is IL of infinite plus IL of 0 minus minus IL of infinite into e raised to power minus t by tau. Okay, this is applicable for t greater than 0 because switching is happening at t equal to 0. So from that presence of ut, you can say that the switching is happening in presence of is happening at t equal to 0. Okay, so what is the data given? So the data given is, we have to find the time, what is the minimum time taken for the current flow to reach 99% of its final values. Which current? The inductor current, right? Current to the inductor. So what is the final value of the inductor? So final value of the inductor means we need to find what is my IL infinite. So at t equals to infinite, the network is in steady state and the inductor is replaced by short circuits, right? So if I do that, so how the situation will be? So the inductor is replaced by short circuit. This is what the inductor is now. And this is I0 ut. Its value is simply I0 at t equals to infinite. I0 ut graph is like this. So at infinite's value is I0. So I0 of current is coming here. So one path resistance is R, other path resistance is 0. So what is going to happen? The entire I0 is going to flow through this path only. Do you agree or not? This entire I0 is going to flow through this path. So IL of infinite, in simple language, it will be your I0 only. This will be your I0. Now, taking this into consideration and by using in the equation which we have written now let's see how does this equation look like now. So my IL of infinite is I0 plus IL of 0 minus is I0 by 5 minus IL of infinite is I0 into e raised to power. Okay, what is tau? Tau is nothing but L by R. In a first order RL circuit, it is L by R. So L value is 1 millihenry, R is 10 kilo ohm. So 1 into 10 raised to power minus 3 divided by 10 into 10 raised to power 3. So it is coming as 1 into 10 raised to power minus 7, I think, isn't it? Yeah. 1 into 10 raised to minus 7. So this is what your time constant. But here you see that we need 1 by tau because e raised to power minus t into 1 by tau. So here it is minus of 10 raised to power minus 7 applicable for t greater than 0. But of course multiplied by t. Because tau is this much means 1 by tau. Okay, so it will be 1 by tau means, so here you will get plus sign spread, isn't it? This is plus. Okay, so this is what is your ILT equation in general. But what I am supposed to find? I am supposed to find the time t so that the inductor current will be 99% of its final value. So its final value is I0. So 99% of final value means 0.99 into I0. So what is that time instant t so that the inductor current will be 0.99 into I0. So in simple language, now we have to just solve this equation and we have to get the value of t. So 0.99 I0 is equals to I0. And how much this is, students? So this is 0.2 and this is minus 1. 0.2 minus 1 is minus 0.8. So I0 minus 0.8 I0 into e raised to power, how much? Minus of 10 raised to power 7t. isn't it? So this term is minus 0.8 I naught, and this is e raised to power minus of 10 raised to power 70. Now you can see this I naught cancels out. So then the equation is 0.99 is equals to how much? 1 minus 0.8 into e raised to power minus of 10 raised to power 70. Now we can easily simplify this for t. So how much you get? So 0.8 into e raised to power minus of 10 raised to power 70 is equals to 1 minus 0.99. So e raised to power minus of 10 raised to power 70 is equals to, so this is 0.01, and this is divided by 0.8. So this implies minus of 10 raised to power 70 is equals to ln of 0.01 divided by 0.8, or t is equals to minus of 1 by 10 to the power 7 into ln of 0.01 divided by 0.8. Okay, you please simplify this, students, and if you simplify this, the value of this t is coming as 0.438. This is coming as 0.438 into 10 raised to power minus 6, or which is 0.438 microsecond. So this is what is the value of t is coming. So because I am explaining, students, I have taken around 5 minutes of time. If you solve this problem in proper flow, it should not be much more than 2 to 3 minutes in the worst case, that too because of the calculation involved, little bit calculation involved. So that's it. It's a very simple problem. Answer is 0.438 for this. This question is asked in gate 23 of instrumentation. This is from network subjects and from coupled circuit topic. The question is, a sinusoidal current I1T is flowing through a 4 Henry inductor which is mutually coupled to another 5 Henry inductor carrying a current of I2T. The coupling coefficient between the inductor is 0.6. The peak energy stored in the circuit is dash microjoule. So student, this is basically a simple formula based problem. Okay, so whenever two coils L1 and L2, okay, which are mutually coupled, in this case the peak energy or E max is given by the well known formula half L1 IM1 square plus half L2 IM2 square plus M into IM1 into IM2. So this is a very standard well-known formula in coupling circuits. Whenever two coils are coupled with this dot conventions, then this is what is the maximum energy stored. The IM1, IM2, these are nothing but your peak value of the current. I mean IM1 will be 1, IM2 will be 2. So here L1, IM1, L2, IM2 are given. The only unknown thing is M. And M is given by the well-known relation M is equal to the coefficient K into square root of L1 into L2. So K value is how much? Yeah, 0.6. So 0.6 into L1 is 4, L2 is 5. This is 4 into 5. So if you solve this, this is coming as how much? 2.68 Henry. This is coming as 2.68 Henry. So now if we substitute these all, half into L1 value is 4 into IM1 value is 1, so 1 square plus half into L2 value is 5 into IM2 square, that is 2 square, plus M we got 2.68, and then IM1 is 1, IM2 is 2. So this, if you check it out, so this is 4 by 2 is coming as 2 only, right? This is 2, and then this one is coming as 10, right? 25 into 4, 20 by 2 is 10, and 2.68 into 1 into 2, so that is coming as 5.36. Okay. So because the currents are in milli, if you square it, it will be automatically in micro units. So this much of microjoule. If you simplify this, This is coming as 17.36 microjoule. So the answer is 17.36. So it's a simple, straightforward formula-based problem, students. Answer is 17.36 for this. This question is asked in Gate 23 of Instrumentation. This is from network subjects and from AC circuit topic. The question is, the voltage source Vs has an internal resistance of 50 ohm. The RMS value of the current through R is dash milliampere. So we are supposed to find the RMS value of this current I. So because this source having internal resistance of 50 ohm, so if I ask you to introduce in the circuit, so it will look like this, because in a practical voltage source, the internal resistance comes in series with the corresponding ideal source. So this is what is the circuit is, and we are supposed to find the current. So first thing is, I'll be finding the impedance of the circuit. So if I find the impedance, there is a single source, that will be series circuits. So V by Z will be my answer for I. Then we can easily find what is the corresponding RMS value. So for that, so let me first find what is the impedance of this inductor. ZL is equals to J omega L. So J into omega is 20,000 pi. So 20,000 pi. L value is 1 by 20 pi into 10 raised to power minus 3. Pi cancel out. So in 25 cancel out, this is coming as 1000, and 1000 into 10 raised to power minus 3 is 1. So it is coming as simply J. ZL is equals to J. Now similarly, what is your ZC? ZC will be 1 by J omega C. So it is minus J into 1 by omega. Again your 20,000 pi, and C value is same, 1 by 20 pi into 10 raised to power minus 3. Again your pi cancel out. So 25 cancel, this is coming 1000. 1000 into 10 raised to power minus 3 is 1. 1 into minus J is minus J. So ZL is J, ZC is minus J. So what is the overall impedance seen from this source, I mean from this point? This is 50 plus 25 plus J plus minus J plus 25. Because all are in series, I am adding 50, 25, J minus J and 25. So naturally J minus J cancel out. So this is simply 100. Z is 100. So if Z is 100, I mean this is the circuit is operating at resonant frequency, because ZL and ZC are getting cancelled out. So what is the overall current? If I say current is IT, your IT will be nothing but VST divided by Z in this case, right? So VST is how much? 10 root 2 sine of how much? 20,000 pi t, right? This is what your VST divided by Z is coming as 100. So if you simplify this, so this is coming how much? This is coming as 0.1. 10 by 100 is 0.1. 0.1 root 2 sine of 20,000 pi t. This is what your IT expression. But we are supposed to find what? We are supposed to find the RMS value of this. So IRMS is nothing but, in a sinusoidal quantity, peak value or maximum value divided by root 2. So it is 0.1 root 2 divided by root 2. So root 2 cancel out. It is coming as 0.1 ampere. So 0.1 ampere, but we are supposed to give the answer in the milliampere units. So 0.1 ampere is equivalent to 100 milliampere. So very simple and a easy straightforward question, students. Answer is 100 for this. Just we have to find the impedance. Okay, it's coming a real quantity. Then we are getting the corresponding answer as 100 milliampere.